Welcome to David Alexander Maths Tuition. This is chapter 3e, sum to infinity. So in a previous chapter we've worked out the sum of n terms of a geometric series. And what we're going to do here is the sum to infinity. Now the sum to infinity is if there are infinite terms. Now this doesn't work for every geometric series. Not every geometric series has a sum to infinity. If we look at this first series, we're doing 3 plus 6 plus 12, so each subsequent term is double the previous one. So we're starting off at 3, then if we're adding 6 to that, that's taking us from 3 up to 9, then we're adding 12, that's taking us up to 21, then we're adding 36, that's taken up to 57. So the sum of this geometric series is getting bigger and bigger and bigger. So if there are infinite terms, then there will be no sum to infinity. The sum to infinity will also be infinite. Now, when there is no sum to infinity, then we call this a divergent series. Now, if there is a sum to infinity, which there is in the second example, it is called a convergent series. Now, for there to be a convergent series, in other words, for there to be a sum to infinity, the common ratio r, so where r is the common ratio, the modulus of r must be less than 1. Okay, so in this particular example, we can see that to go from 1 to the next, we are multiplying by 0.5. So here, that is less than 1, and this works. So 16, if we're adding 8 to that, that would take us up to 24. If I add another 4 onto that, so we started at 16, we've gone to 24. If I add 4, that will be 28. Add another 2, that will take me to 30. Plus 1, 31, 31.5, 31.75. So we can see that this series will be tending towards a certain value. This series will never reach, a million. It will never reach 100. It will never reach 40. So this series does have a sum to infinity because it's a convergent series, and that is because the common ratio r, or the modulus of r, is less than 1. So we know that the sum of the first n terms of a geometric series is a lots of 1 minus r to the n over 1 minus r, where a is your first term, r is your common ratio, and n is the number of terms. The sum to infinity, which can be written like this, s infinity, is a much simpler formula. It's just a over 1 minus r. And remember, this only works when the modulus of r is less than 1. Okay, so let's look at a few examples. So we're trying to work out the sum to infinity of a geometric series with first term 50 and common ratio -1/4. So the sum to infinity is a over 1 take away r. So that is a is our first term, which is 50, over 1 minus r, so that's 1 minus -0.25. So in other words, that is the sum to infinity is 50 over 1.25, and 50 divided by 1.25 is 40. So the sum to infinity is 40. It's a slightly different one. Here we're working backwards from the sum to infinity. So the sum to infinity is a over 1 minus r. So 100 equals a, which is 50 over 1 minus r. I'm going to multiply through by 1 minus r. So 100 lots of 1 minus r equals 50. I'll expand the bracket. So 100 take away 100r equals 50. Subtract the 100. So negative 100r equals negative 50. So 100r is positive 50. So r is 50 over 100. R is 1/2. Okay, so here, again, working backwards to find the first term. So the sum to infinity is a over 1 minus r. Here the sum to infinity is 10. We want to work out the first term. We want to work out a. So that's 1 take away 1/3. So that's 10 equals a over 2/3. So 10 multiplied by 2/3 is a. So a is 20 over 3. Okay, for this question we've been given 2 bits of information. The sum of the first 3 terms is 32.5 and the sum to infinity is 32. So the sum to infinity is a over 1 minus r. So 32 equals a over 1 take away r. Now the sum of the first three terms, well, the sum to the first n terms is Sn is a lots of 1 minus r to the n over 1 take away r. So S3, that is going to be 32.5 is a, which we don't know, 1 minus r, which we don't know, but n is 3 over 1 minus r. Okay, so what I need to do is somehow do a bit of substituting perhaps. So I know that a over 1 minus r is 32. Now here I've got a over 1 minus r. So if I can replace that with 32, I'm away. So 32.5 is 32 lots of 1 minus r cubed. So I'm going to expand those brackets. So 32.5 is 32 take away 32 r cubed. I'm going to subtract 32 from both sides. So 0.5 is negative 32 r cubed. So 0.5 divided by negative 32 is r cubed. So 0.5 divided by 32 is 1 over 64, or minus 1 over 64. So therefore r is going to be the cube root of that. So minus 1 over 64 and cube root of that. So r is negative 1/4. Okay, so I found the common ratio. Now it's going to be relatively easy to find out what a is. So 32 multiplied by 1 minus r equals a. And I know that r is negative 1/4, so that's going to be 32 lots of 1 minus 1/4. In other words, 32 multiplied by 1 1/4, or 1.25, or 5 over 4. So therefore a is 32 multiplied by 1.25, so a is 40. So the first term is 40 and the common ratio is negative 1/4. Okay, so here's looks like a hard question because there's lots of stuff to it, but actually it's fairly straightforward. So the first part, we've been given the common ratio. Well, we need to show that it's 0.8. So we know that a over 1 minus r must equal 50. So therefore what we can say is that 10 over 1 minus r is 50. So therefore what I can do is just swap these around. So 10 over 50 is 1 take away r. 10 over 50 is 0.2, so 1 minus r is 0.2. So negative r, take away 1 from both sides, is negative 0.8. Therefore r is 0.8, which is what we were aiming for. Okay, find to three significant figures the difference between the 9th and the 10th term. So remember, in a geometric series, first term is a, then ar squared. So the third term is ar to the 2. So the 9th term, that is going to be ar to the 8, and the 10th term is ar to the 9. So for the 9th term, my calculation is going to be a, which is 10, multiplied by 0.8 to the 8. And the 10th term, that is going to be 10 times by 0.8 to the power of 9. So let's work these out. So for the 9th term is 1.67777216. And the 10th term is 1.34217728. So therefore the difference is, well, the bigger one, take away the smaller one. So the difference is 0.33554. So to three significant figures, that is 0.336. The sum of the first 14 terms, so the sum of n terms is always a lots of 1 minus r to the n over 1 minus r. It's sorry, that's a 1 there, not another r. So actually the sum of the first n terms is a more complicated formula than the sum to infinity. So a, we know, is 10, 1 take away r, which is 0.8. So here n is 14, all over 1 take away r, and so that's 1 take away 0.8, or 0.2. So type all that into the calculator and you should end up with 47.800097674. Okay. Okay, for the final part of the question, I know the formula for the sum of the first n terms, That's a lots of 1 minus r to the n over 1 minus r. But rather than making it greater than 23, I'm going to make it equal 23. So what I can say is, well, I just need to substitute in my values. So 10 lots of 1 minus the common ratio, which is 0.8 to the power of n. N is what we're trying to work out, over 1 take away 0.8, which is 0.2, equals 23. As I'm running out of space here, I'm just going to multiply by 0.2. That gets rid of that 0.2. And I'm going to divide by 10. And 23 multiplied by 0.2, that is 0.46, I believe. 23 times 0.2 divided by 10, 0.46. Okay, so 1 take away 0.8 to the power of n equals 0.46. I'm going to subtract the 1, so negative 0.8 to the power of n is negative 0.54. So 0.8 to the power of n is positive 0.54. So therefore n is log base 0.8 of 0.54. So log base 0.8, 0.54. So n is 2.76. Okay, so if there were exactly 2.76 terms in the sequence, which obviously doesn't make sense, then we would be getting exactly 23. So for the first, so if I'm getting greater than 23, then that is going to have to be rounded up to 3. So here n is 3. And we can check this out. The first term is 10. So the second term is 10 multiplied by 0.8. So 10 times 0.8 is 8. 8 times by 0.8 is 6.4. Okay, so if I add the first two terms together, I get 18. That's not greater than 23. And 18 plus 6.4 is 24.4. So we can see that it's 3 terms. It's the sum of the first 3 terms that gives me this total, which is greater than 23. So we can check it. It was quite easy to check because we were only looking for adding up the first 3 terms. Perhaps a different story if n was 13, that would perhaps be a bit more of a pain, but still doable anyway.